Good morning. So, coming to discrete mathematics subject, unit 1 will start discussing this part, logic and set theory. In that also today's session will be introductory, wherein we'll be discussing logic, few truth tables, propositional equivalences, predicates and quantifiers. This is our prescribed textbook by Kenneth H. Rosen for discrete mathematics, and 7th edition we are using. The contents are derived from this and other notes I am referring. So, what exactly is discrete mathematics? So, discrete mathematics, it is part of mathematics. It will be studying discrete objects, right? And what is the meaning of discrete objects? They are distinct, they are unconnected elements. So, what kind of real time things can be connected with discrete mathematics are like, suppose, what are the different ways of setting a password, what are the probabilities of winning a lottery, is there a link between two computers in a network, how to identify spam email messages, how do I encrypt the message, what is the shortest path between two cities. So these kind of answers we can derive by knowing the concepts of discrete mathematics and the related computing subjects. So why I should study discrete mathematics is to increase or develop my mathematical maturity. That is my ability to understand and create mathematical arguments. Discrete mathematics is the gateway to more advanced courses in all parts of the mathematical sciences. It provides mathematical foundation for many computer science courses, including data structures, algorithms, database theory, automata theory, formal languages, compiler theory, computer security, operating system, and many more. The basic building blocks of logic are propositions. What is a proposition? It is a declarative statement. That is, it declares a fact. And what is a declaration? The fact that it is either true or false, but not both. For example, the following four sentences. Among the following four sentences, 1, 2, 3, 4, which are also called as propositions, 1 and 3 are true. 1 and 3 are true, while 2 and 4 are false. Why 1 and 3 are true? Let us check. So Washington DC is the capital of United States of America. That is a true fact. Third one is 1 plus 1 is equal to 2. That is a true. So the proposition number 1 and proposition number 3 are true. While we know that Toronto is not the capital of Canada, so proposition 2 is false. While we also know that 2 plus 2 is not 3, so proposition 4 also is false. Now coming to these four propositions, what time is it? Read this carefully. X plus 1 equal to 2, x plus y is equal to z. So all of them are not propositions, because what is the premise for proposition? They are declarative. What is the premise for declaration? Declarative statements, they are either true or false. If I look at sentence number 1, what time is it? I don't know whether it is it is not falling under true or false. Read this carefully. It is not falling under true or false. X plus 1 equal to 2, it may be false, it may be true. X plus y is equal to z, it may be true, it may be false. This symbol which we are seeing here is a negation symbol, and P, we can let us say this is a proposition. So negation of this P, negation of a proposition. So if the proposition is true, the negation of that is false. If it is false, the negation of that is true. We are seeing a truth table for the negation of proposition. If you see this symbol, you immediately say that it stands for conjunction, and it stands for and. So you call it as P and Q. Okay. And if you see this symbol, you will say that this is for OR, and this is for disjunction. So let us look at the truth table for conjunction. What it says, uh, conjunction means both the values should be true for the output to be true. So true, true, output is true, or else all are false. Disjunction means OR means any one of the values should be true for the output to be true. This is for disjunction. What about XOR? I am finding if the values in the input are truth values, then the output is false. The truth value can be true or false. So you can see the first row here, both are truth values, so the output is false. Both are false values, so the output is false. So in case of XOR, if both the inputs are truth values, the output is false. Okay. This stands for implication. P implies Q. It comes under conditional statements. The left side of this implication symbol is called as the hypothesis, or it is also called as the antecedent, or it is also called as a premise, while the right side symbol Q is called as the conclusion or a consequence. So if P implies Q is there, and if we write Q implies P, that is called as the converse of P implies Q. So if P implies Q is there, and if you write not Q implies not P, then it is called as contrapositive. And if you write not P implies not Q, then it is called as inverse. Now coming to implication, P implies Q, this is my implication, P implies Q. So for P implies Q, what the truth table says, for P implies Q, the truth table says is that if P is true and Q is false, then P implies Q is false. So if P is true, Q is false, then P implies Q is false. So let us look at such combination. So in the second row, we see that P is true and Q is false. Then the P implies Q is false. Now coming to biconditional, this is a symbol for biconditional. So the truth table for biconditional P implies Q will be like this. If P and Q have both truth values, then the output will be true, else it will be false. So it is kind of opposite to our XOR which we have seen. So let us see the truth values of P and Q. First record are true and the last record are true. So for both of them the output is true. Now comes few examples wherein we need to construct the truth tables. So what we have to do is we have to put this P and Q in the truth table, and we have to just simplify this by finding out first not of Q. Once I found this not of Q, then P or if not of Q I'll find out. After that I'll be finding out P and Q, and once we did that, this will left part will be called as P and the right side will be called as Q, and P implies Q, and for P implies Q we know we have to use this truth table. If P is true, Q is false, then P implies Q is false. So that using that truth table you can simplify this. Coming to the precedence of the operators, negation has the highest precedence. After comes the AND conjunction, after comes the OR disjunction, after comes the implication conditional statement, and then comes the biconditional statement. So this is what is the precedence of the operators. Now these truth values and false values in logic, if you want to represent in the bit forms, true is given as 1 and false is given as 0. Now we also know that AND or XOR can be used as connectives, they are also called as logical connectives. So this symbols AND or XOR can be represented like this also, OR, AND and XOR. Now we also know the truth tables for AND operation, OR operation and XOR operation, which we had seen previously. Same holds true here. So OR will be any one input is true, output will be true. AND will be both the inputs are true, output will be true. XOR will be the truth values. If the inputs have truth values, the output will be false. Now, you can see this example also. We are finding out here OR, AND and XOR, which we can quickly just verify once. For example, AND, both the inputs are 1, the output is 1. If one of in OR both the inputs are one of the input is 1, the output will be 1 kind of thing. And in XOR, we have already seen the performance of XOR. This is the premise for XOR. If both truth values, input truth values are there, the output will be false. So for XOR also, if both truth values are there, output value will be false. For example, this is false. Then these two inputs are truth value, this is false. Then these two inputs are truth value, this is false. These two input values are truth value, this is false. So this is how we'll find out the bitwise OR and XOR. Now we have understood a little bit of propositional logic, but what are the applications of propositional logic? Okay, they can be applied in mathematics, computer science, and many more disciplines. Okay, natural languages, NLP, natural language processing rather, because natural languages are quite ambiguous and quite imprecise. Okay, to make them precise, to make them unambiguous, we need to convert those into logic. Okay, so that's why logic is used in specification of software and hardware, in computer circuit design, designing a computer program, verification of the correctness of the program, building of expert systems. Logic can also be used to analyze and solve familiar puzzles. Uh, Many software systems are based on rules of logic, but not all. Now, coming to propositional equivalence, this is a very interesting aspect. If there is a compound proposition and the output of that is true, okay, whatever may be the truth values inside, then it is a tautology. If the output is false, then it's a contradiction. If the output is neither true nor false, then it's a contingency. So, for example, P or not P is always true, it's a tautology. P and not P is always false, it's a contradiction. Let us look at this De Morgan's law. De Morgan's law, what it states, not of P or Q implies not of P and not of Q, and not of P and Q implies not of P or not of Q. So using this De Morgan's law, we can show logical equivalence of these two kind of things. So what we have done here, not of P or Q and not of P and not of Q. For that, we first found out P or Q, then not of P or Q, then not of P and not of Q, and not of Q and not of Q, not of P and not of Q, we have taken the output. So we just have to compare these last columns. So false, 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 true, false, 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 true. So they are logically equivalent. So similarly, we can find out whether these two are logically equivalent or not. You can again check whether these two are logically equivalent or not. These are the examples which you can solve by simplification and comparison. You can see here this P R in the bracket Q and R, and there is one more P or Q and P or R. Actually, this is the distributive law of disjunction over conjunction. We need to show that they are logically equivalent. These are few of the logical equivalences. We'll go with simplest, De Morgan's law. Not P and Q implies not P or not Q. Not P or Q implies not P and not Q. Let us go for the commutative law. P or Q implies Q or P. P and Q implies Q and P. Associative law, P or Q or R will be equal to P or Q or R. P and Q and R will be equal to P and Q and R. Double negation law stands here, not of P equal to P. So idempotent law stands here, P or P equal to P, P and P equal to P. You have identity law, P and any truth value will be equal to P. P or a false value will be equal to P. Domination law, P or true equal to true, P and false equal to false. You have negation laws also, P or not P equal to true, P and not P equal to false. There is a small example here wherein we need to check whether this is a tautology or not. Okay, so what we are doing, so this can be actually this, if you treat this as a P and if you treat this as Q, this will be P implies Q or A implies B kind of thing. So this, which can be represented not of A or B. So first we are going to simplify this by putting not of A or B fashion. Then not we are applying to this bracket and not P or not Q by De Morgan's law, and then we are just making a rearrangement using associative and commutative laws, and what we get is not P or P or not Q or Q. So irrespective of the truth values, the output is true. So and that's why we are coming it to be a tautology. What is a predicate? Suppose there is a statement called as x is greater than 3. Here x is the statement and the second part is greater than 3 will be the predicate. What is a predicate? It refers to a property that the subject of the statement have. So if I write P of x, here P denote the predicate and x is the variable, and let us say is greater than 3 holds, and if I give P of 2 and P of 4, so P of 4 will be true and P of 2 will be false. What is a quantifier? The extent to which a predicate is true over a range of elements. You have universal quantifiers, you have existential quantifiers, which will be telling the range. So when I discuss logic with the help of predicates and quantifiers, it is called as predicate calculus. Okay. For example, here this is the universal quantifier for all x, and this is the existential quantifier, there exists x. So for all x, px denotes the universal quantification. So for all x, px, this is true for every x. There exists x, px, this is true for an x. So there is a uniqueness quantifier also. It is denoted like this. There exists a unique x such that p of x is true. We can convert our English sentences into logical expressions using these quantifiers. Every student in this class has studied calculus. For all x, student x, calculus x. Some student in this class has visited Mexico. There exists x, some student x and Mexico x. Every student in this class has visited either Canada or Mexico. For all x, student x implies Canada x or Mexico x. So with this we'll stop today's discussion.